Okay, I think it has quieted down, so let's get started.
Okay, excellent. Thank you. Okay, so welcome all, and thank you for coming to this session. Thanks to the organizers for inviting me to speak about this. So what I wanted to tell you about today is this very exciting proximity prize that I hope all of you can contribute to. And as the title says, there are prizes to be won here. This is based on joint work with Gal Arnon and Giacomo Fenzi. We just put out this paper that surveys the area and defines the prize. It's up on ePrint. It will also be on the Proximity Prize website. So I highly encourage you to kind of look at this paper. It goes into much more depth than what I have time to go into in this talk. So to start with, I actually wanted to make a list of all the papers that I want to talk about in this talk. And so I started making this list, and I kind of gave up when the font became too small. Yeah, so I try to list all the papers that are the most relevant, but this is by far an incomplete list. And of course, please take a look at the full paper for the complete list. But you can see there's kind of enormous amount of work on these proximity gaps, starting back from the classic works in 2013 and so on. And so I just wanted you to have a bit of a bibliography, but with that we can get started. So what is the Proximity Prize? So the Proximity Prize is $1 million prize. We don't have too many $1 million prizes in mathematics, so this is like a wonderful thing to see. It's actually thanks to the Ethereum Foundation. It's kind of spearheaded by Justin Drake, so thank you, Justin, for making this real. And the judges are myself, Giacomo, and Gal, and so we're looking forward to seeing lots of proposals or lots of solutions from all of you. And as you can see, there are prizes to be won here. Okay, so what is the Proximity Prize and what is the Proximity Challenge? What is all the excitement about? The cool thing about this, it's really just a question about polynomials. Yeah, it doesn't involve any fancy algebra. There's no schemes, no sheaves. It's literally something that Gauss could have worked on if he was so interested. It's just a question about polynomials. So you might be wondering, well, why is the Ethereum Foundation paying $1 million to solve a question about polynomials? And as you probably all know, if we can actually prove that this conjecture is true, then we get better provable systems, better provable snarks based on Reed-Solomon codes. Yeah, so I think it's really quite commendable from the Ethereum Foundation. They want to kind of minimize the number of conjectures in the systems that run the blockchain, and this is kind of a way to do that. Yeah, so everybody needs to prove this so that we can eliminate an important conjecture in the development of snarks for the purpose of blockchains. Okay, so far so good. So that's kind of the high-level settings. So now you wonder, well, what is the proximity challenge? Like, what is the problem that we're trying to solve? And so let me just show you. So if you open up the first page in the paper, basically we list these two grand challenges. So I don't want you to read this. All I'll tell you, the reason I put this up here is I just wanted you to see the statement of the challenge. The statement of the challenge is about Reed-Solomon codes. These are constant rate Reed-Solomon codes over smooth domains, which we'll talk about in just a second. And the problem really is, can you identify the largest distance delta such that the mutual correlation error for the code C at this distance is basically negligible? Yeah, that's the whole challenge in just a few words. Find the largest delta, prove that it's the largest delta. That makes the mutual correlation error be negligible. So that's one grand challenge. And the other grand challenge has to do with the standard list decoding problem in coding theory, which again applies to Reed-Solomon codes. The challenge is, can you find the largest delta such that when I give you a Reed-Solomon code, the list decoding size of the code at this distance is also negligible in the size of the field. Yeah, it's the size of the field divided by this fraction. Yeah, so these are the two grand challenges. I can tell you that there are a lot of connections between mutual correlated agreement and list decoding sizes. But as we know, with everything we know today, these are kind of two independent challenges. It would be great if one challenge implied the other, but right now these are kind of two independent challenges. So now you're probably saying, well, who cares? Why are these grand challenges important? And more importantly, I just said a whole bunch of words, but what do these words even mean? Yeah, like I imagine not everybody here even knows what the mutual correlated agreement is, or maybe even list decoding. And so what does this mean? Why is it important? And that's what I wanted to talk about in this lecture. Yeah. So I'll start with what do all these words mean? Like I'll unpack the grand challenge for you, so that you can understand what the problem is. And then hopefully I'll have time at the end and I'll show you a little bit about why this is important. And actually there will be many talks throughout the day today that also talk about why these problems are important. All right, so let's get started. Let's see. So what did these grand challenge actually mean, and what is the problem that we need to solve? So just to introduce some notation, I'm going to use RS for Reed-Solomon codes. So this is a Reed-Solomon code over a field F with an evaluation domain L. This is the domain where we evaluate the polynomial at, and the degree of the polynomial is going to be at most k. Yeah. So this is a linear subspace of f to the size of the domain. So Reed-Solomon code over a smooth domain. Smooth domain just means that the size of the domain is a power of 2, and it happens to be a subgroup or a coset of a subgroup. We're mostly interested in constant rate codes. Yeah. So the rate of the code needs to be kind of a reasonable fraction. And that's kind of where we're going to focus. I'm also going to use delta min. Oh, I hope everybody can see what I wrote down there. I'm going to use delta min as what's called the minimum relative distance of the code. It's just the minimum distance of the code divided by the length of the code. So it's some fraction between 0 and 1, just to set the terminology. Okay, before we go any further, I have to remind you a little bit about list decoding and some of the bounds that are known for list decoding. I imagine many of you already know this, but let me just quickly make sure everybody's on the same page. So quickly to remind you the Johnson bound. So the Johnson bound is some function of the code. So I'll use J of C to denote the Johnson bound of the code. I wrote what the expression is for J of C here, but the expression doesn't matter so much. So for distances between 0 and the Johnson bound, we know that the list decoding size for the code at that distance is some small function of delta. So what is the list decoding set here? This is basically the largest possible number of code words that are close, that are delta close to a particular word. And we know that as long as delta is less than the Johnson bound, the size of this list is going to be some small function of delta. Yeah, so again, I imagine many of you have heard of the Johnson bound. That basically says how far away from the code can we get so that the possible set of close by code words is not too large. The only thing that's important to note is that this function, the size of the list, this function sort of blows up, goes to infinity as delta approaches the Johnson bound. Yeah, so up until the Johnson bound, we know the lists are well behaved. As you get closer and closer to the Johnson bound, all of a sudden, these lists get bigger and bigger and bigger. So really, the picture I want you to have in mind is if we are below the unique decoding distance of the code, this is delta over 2, the size of the list is always less than 1. There's only one code word close to a given word. As we get closer to the Johnson bound, we know that the size of the list is still well behaved. We know that above what's called the alias radius, which is roughly the minimum size of the code, when we go above the minimum size of the code, we know that the size of these lists kind of explode. And as you probably know, there's a big open question as to what happens to the list decoding bound when we're between the Johnson bound and the capacity of the code. Yeah. So this is it's kind of unknown what this behavior is, and actually this is one of the grand challenges. Resolve this major long-standing open problem on Reed-Solomon codes. What we do know is that if we use a random Reed-Solomon code, that is the evaluation domain is a random set, then we know that this is actually that the list decoding bound is well behaved even in this unknown interval. And the same is true for these things called subspace design codes, of which folded Reed-Solomon is one example. Yeah, so there are variants of Reed-Solomon codes for this is well behaved, for which this list decoding bound is well behaved here. But overall, we'd actually, for codes, Reed-Solomon codes of interest to us, it's actually unknown what the behavior of list decoding here is in this interval. So far, so good. I hope this is just a quick review for everybody. I hope everybody's familiar with these notions already. Okay, good. So now I'm going to actually say a few more words. I'm going to throw some words at you, and then we'll kind of interpret them as we continue. Okay, so I want to talk about 5 notions of proximity gaps. Yeah. So the basic notion of a proximity gap is called proximity gap. Yeah. I'm not going to define that just yet. So let's leave it at that. But then it turns out there's actually a stronger notion of a proximity gap, which is actually more useful in the design of snarks, and this is what's called correlated agreement. Yeah, so again, I'm not going to define it just yet. We'll come back to it in just a second. It turns out correlated agreement is already enough to analyze some variant, simplified variant of FRI. To actually analyze the real FRI, we need a little bit more than correlated agreement. Then it turns out there's even a stronger notion of correlated agreement called correlated agreement with linear constraints. Yeah, this is due to Habak. So correlated agreement with linear constraints refers to correlated agreement when we focus on a subspace of the Reed-Solomon code, and it turns out that's actually already sufficient for analyzing basefold and Weir-like constructions. Okay, so far I'm just saying words. We'll make sense of them in just a minute. There's even a stronger notion of a proximity gap called mutual correlated agreement, which is kind of what's important to us. And it turns out that that actually gives us a very simple extractor for things like basefold and Weir. And finally, there's something called line decoding. Yeah, line decoding, which oddly this is kind of the strongest notion of a proximity gap that we have. And oddly, when you look at what coding theorists do, this is actually what they prove. Yeah, so line decoding is actually what the coding theorists prove for us, and that implies all the other notions of proximity gaps. Yeah, so I think this is kind of a nice picture to show the different types of proximity gaps that are out there. What I want you to remember is actually what people actually prove, that what the coding theorists actually prove is the strongest notion that implies all the other ones. Okay, because of that, and because I only have limited time, I'm actually going to only talk about kind of the strongest two notions. I'll talk about line decoding and I'll talk about MCA. I'm kind of not going to talk about the other three today. That's in the paper. All the results about the other three are in the paper. So we're just going to focus on these two. I'd like to make actually a controversial statement, which is that because the coding theorists prove line decoding, which is the strongest notion, actually we might as well forget about the three other notions of proximity gaps down the chart there and just focus on MCA, mutual correlated agreement. MCA turns out to be like a really useful notion for analyzing snark systems, and that's kind of the one that we should be focusing on, and that's actually what we're going to talk about in this talk. So far, so good. Nobody wants to shoot me for saying this, hopefully. And so we're going to focus on line decoding and mutual correlated agreement. All right. So far I just said a whole bunch of words. I'm not sure it made sense to many of you, but let's kind of go and define what these things are. So now we start our story. Kind of the talk begins now. So the starting point that I want to talk about is this first notion, this line decoding notion. And so, yeah, let's talk about what does it mean for a code to be line decodable. I think it's a really beautiful notion. The first time it's actually written as a LaTeX definition block, oddly, is in this paper by Goel and Guruswamy, just from earlier just from last November. Although this notion of line decodability was kind of in the air for many times. Yeah, in many earlier papers, it's just kind of formally defined in this very recent paper. So what does line decoding actually mean? It's kind of a very elegant and beautiful notion. So let me explain what it says. So we'll say that a linear code is line decodable. We'll parameterize it by distance delta, and then these two other variables, a and b. So we'll say that it's line decodable if it's true that for every line in the space, yeah, so this is a line in f to the n. Remember, our code lives in f to the n. So it's a linear subspace of f to the n. We can look at lines in f to the n. Yeah, just think of a simple line in the space f to the n. Every line has the following property. If there are a code words that are delta close to the codes on the line, yeah, so there are a code words that have there are a words on the line that have code words at distances at most delta, then it must follow that b of those close by code words actually are collinear. Okay? It's a very, very simple property. Let's do it visually. I mean, this talk is going to be very visual, so let's do this visually. So we have our line here, and the line has a bunch of words on it, not code words, just arbitrary words. Let's suppose that there are a close by words, so the little green squares are going to be code words. So let's suppose that there are a close code words that are close to this line.
then it so happens that B of them must be collinear. That's the whole property. Yeah, so if we have A close by code words, B of them have to be on a line. This is, I really want you to remember this definition, so let's do this one more time. Yeah, I believe in learning by repetition, so let's say it one more time. So we have an arbitrary line in f to the n. The line in f to the n has a bunch of words on it. There are A code words that are close to this line, and because there are A code words close to the line, some fraction of them, some B subset of them must be collinear. They must be on another line. Okay? That's the property that's called line decodability. Yes, the code satisfies this property. We'll say that it's delta AB line decodable. Delta, again, is the measure of distance. So far, so good? That's this kind of quite elegant notion. All right. So more generally, we can talk about, actually, I'm going to only talk about line decoding. When we look at lines, more generally, you can talk about curves, where maybe we don't just, a line is a linear combination of 2 points. You can imagine linear combinations or even curved combinations of more points. But for this talk, we'll just focus on line decoding and not curve decoding. Again, in the papers, you can look at the more general curve decoding notion. Okay, so now we have this notion of line decodability. The question is, what do we know, for example, about the Reed-Solomon code, the line decoding property of the Reed-Solomon code? So here I think there's something really interesting happening. There are these classical results, I would say ancient results from 2020, for example. This is ancient in this field. The famous BCIKS result, there's an improvement of the BCIKS result that just appeared last November that kind of tell you something about, these results were originally stated in terms of correlated agreement. Remember, correlated agreement was the second level of the proximity definitions. But it turns out what these papers actually prove is a much stronger statement. What they actually prove is that the Reed-Solomon code is line decodable in the sense that we just saw. So I'm going to rephrase these classical theorems in terms of line decodability. Yeah? And yeah, so this is actually, this rephrasing is due to a recent paper. The Stu paper actually shows it this way. And so, well, let's see what it is. So basically, for the Reed-Solomon code, it so happens that if the distance happens to be between the unique decoding bound and the Johnson bound, it turns out the Reed-Solomon code is AB line decodable for these two parameters that I wrote over here. Yeah, so I guess the actual values of these functions maybe doesn't matter so much. The point is, if A is bigger than some linear function of n, then B is basically A divided by some other function of delta. Maybe the exact value of the function doesn't matter. The only thing I want you to take away from this is that this function blows up as the distance approaches the Johnson bound. Yeah. So AB decodability kind of works well when we're below the Johnson bound. When we get closer to the Johnson bound, sort of everything blows up, and we know nothing about line decodability when we approach the Johnson bound. Okay, so far so good. So we know that the Reed-Solomon code has this nice line decodability property up to the Johnson bound. So one thing that's interesting is, A here is potentially, the field could be quite large. So A here is actually, A is only proportional to the length of the code. It's actually much, much smaller than the length of the field, which is going to be important in a second. And you might be wondering, I kind of told you that the Reed-Solomon code is line decodable up to the Johnson bound. So now you might be wondering, well, what happens above the Johnson bound? And that is a great question. In fact, it's such a great question that it's worth $1 million. Yeah? So if any one of you, please, if any one of you can figure out what happens to line decodability above the Johnson bound, the three of us will be your friends forever, and you'll walk away with some prize money as well. So this is a really beautiful, so you can see the line decoding notion is a very natural notion. And it's just really a question of analyzing what happens to line decodability when the distance goes above the Johnson bound. Really very, very interesting question to work on. All right, so far so good? Okay, so why are we talking about line decodability? It turns out the property we're actually interested in is a very important property called mutual correlated agreement. So mutual correlated agreement was first defined in this ACFY paper, the Weir paper, by Arnon, Chiesa, Fenzi, and Yogev. This is the notion that actually is used for analyzing so many of the snark systems that we have out there. Okay, so let me try to define this notion for you. Takes a little bit of work to define it, so we'll go slowly. Then our challenge is to show basically that line decoding implies this beautiful mutual correlated agreement notion. Okay, so let's do it. So to define mutual correlated agreements, I like to define it in terms of this notion called S delta closeness. So we know what does it mean for a word to be delta close to a code. Yeah, there exists some code word that's delta close to the word. S delta closeness just means that it's not only close to the code, it's also close relative to the coordinates in the set S. Okay, so I give you a set of coordinates in the code word or in the word, and basically the word U and the close by code word, they agree on the coordinates in the set S. Again, in the picture, it's really quite to see what's happening here. I give you a word U, there's a close by code word C. They happen to agree on the set S, and the set S is sufficiently large. Yeah, it's just larger than 1 minus delta times n. Then we'll say that U is S delta close to the code. So why is S delta an important notion, a useful notion? Well, first of all, because U and C agree on so many coordinates, we know that the distance between U and C is small. More importantly, when they agree on a set of coordinate S, we know that if U and V are both S delta close to the code, then in fact any linear combination of U and V is also S delta close to the code. Yeah, that's kind of easy to see. They all agree on the same set of coordinates. So if we take a linear combination, the linear combination will also agree on that set of coordinates. Okay, that's just S delta closeness. So with that, we can define mutual correlated agreements. Again, it's a fairly natural notion. And so let's see what it says. Basically, what we'll say that a code has mutual correlated agreements if the following property holds. It should be that, again, for every line in our space, so here I just wrote down an equation for a line that's generated by U0 and U1, the property we have is that every point on the line, if it happens to be S delta close to the code, then the generators of the line are also S delta close to the code. Yeah, that's the whole thing. That's the whole property. So let's just stare at this for one more second. Oh, maybe I should say one more thing. So this property should hold again if a point on the line is S delta close to the code, then the generators of the line should also be S delta close to the code, up to a couple of points where this might not hold. Yeah, so there's an error. Oh man, I hope everybody can see the slides at the bottom of the slide here. But effectively, we want this property to hold, except for a small number of exceptional points, and that's what we call the MCA error. Yeah, and the goal is to prove that the MCA error is small. All right, excellent. So let me just stare at. Let's do this visually, and then I'll make a couple more comments about this definition. So let's look at the definition more visually. So we have our line that has a bunch of words on it. What the mutual correlated agreement property says is if I have a point that's close to the line, so I have a point here or a code word that's S delta close to the line, it's that the fact that it's close to the line means that in fact the generators of the line, U0 and U1, are also S delta close to the code. Yeah, the fact that it's close to the line means the generators are, the fact that this point is close to the code means that the generators of the line are also close to the code relative to the same set S. Actually, let me say that one more time. It's kind of important to get this right. So we have a point in the line. The point happens to be S delta close to a code word. All right? That implies, just that fact implies that the generators of the line U0 and U1 are also S delta close to the code words. Now, if the generators of the line are S delta close to the code words, that actually means that the entire line is close to the code. Yeah, because linear combinations if 2 points are S delta close, their linear combinations are also S delta close. Okay, very good, very good. So in the case of unique decoding, basically there's nothing more to say because every point on the line only has one code word close to it. In the case of list decoding, there could be other code words that are close to the line. Yeah, so here's another code word that's close to the line. It happens to be S prime delta close to the line. Well, that by the mutual correlated agreement property, that should imply that the generators of the line are now also S prime delta close to the code. Okay, and so on and so forth. If we have another point that's close, if we have another code word that's close to the line, this one happens to actually not imply the generators are not S prime delta close, so that's an MCA error. Okay, so there should just be a small number of exceptional points, but all the other points will satisfy the MCA property. So let me say it slightly differently, in that we know that if U0 and U1 are S delta close to the code, then all the points on the line must be S delta close to the code. What MCA says is the converse of that. Yeah, if I have a code word that's close to the line, it must be that the reason it's close to the line is because U0 and U1 are close exactly with respect to the same set. Okay, so there's only kind of one reason why a code word is close to the line, and it's because the generators of the line are close with respect to the same set. Okay, so that's the MCA property. Seems like it's a very elegant property, and as we'll see in just a minute, it turns out to be exactly the right property that's needed for analyzing lots of snark constructions, like basefold and Weir and many, many others as well. Okay, so far so good. So we have these two notions. We have the notion of line decodability, and we have a notion of MCA. I kind of showed you in the first picture that line decodability implies MCA, but when you just write down these two definitions, they seem to have nothing with one another. Why? They seem to not be related at all. So let me state the relation theorem. The relation theorem basically moves us from collinearity to agreement, and the theorem says if a line is A n plus 1 line decodable, yeah, so remember if A points are on the line, n plus 1 of those points must be collinear, that implies that the MCA error is at most A over F. Yeah? So this is a beautiful theorem, really quite cool. Yeah, so if we can prove line decodability, which is what the coding theorists do for us, we automatically get nice MCA error bounds, which is what we need for analyzing snarks. Okay, so this is such an elegant theorem that actually I want to go through the proof. Yeah, it's a very easy proof, so let's just prove this fact is true. You know, there's this rule of thumb that every talk is supposed to have one proof and one open problem. So let's do a proof. All right? It's not too difficult. So let's go ahead and prove this bound. So we're going to prove it by contradiction. Okay, so suppose that the MCA error is actually greater than or equal to A over F. That means that we have A points on the line for which the MCA property doesn't hold. All right, so we have some A points on the line that are MCA errors. What does it mean that they're MCA errors? It means that these A points are close to the code, but the generators of the line are not S delta close with the same set S. Okay, so we have, in particular, we have A points that are delta close to the code. So what do we know? If we have A points that are delta close to the code, that means that n plus 1 of those code words, of the close by code words, must be collinear with one another. Yeah, that's basically what line decoding gives us. Okay, so yeah, so we have n plus 1 points that are on the line. Each one of those points happens to be Si delta close to the code with respect to some set S. And we know that these n plus 1 close by code words, we know that they're collinear. All right, that's literally what line decodability gives us. So far, we didn't do anything. We just kind of used the line decoding property. Well, now there's a small observation, which is to say, if we have n plus 1 subsets of coordinates, right? Our code words are length n, so we have n plus 1 subsets of a set of size n. That implies that there must be some I star such that Si star is contained in the union of all the other sets. Why is that? Well, if Si is not contained in the union of all other sets, that means that there must be some point in Si which is unique to Si and not contained in all the other sets. But we have n plus 1 sets and only n points, so it can't be that every set has a unique point that's not contained in all other sets. Yeah? So there must be some set Si star that's contained in the union of all the other sets. Okay, and this is where now we're going to use the collinearity of the close by code words. That means that this is like a simple observation. that the generators of the line, U0 and U1, must be in particular SI star delta close to the code. Yeah, this is maybe takes a second to see why, but it's actually fairly easy to see why. And if that's true, that means that PI star is actually not an MCA error, but we assumed that PI star actually is an MCA error, so that's our contradiction. All right? So that's it. That's the 4-line proof that this is true. So it shows you that this line decoding property, which is a very simple property to state, right? If A points are on a line, if A points are close to the code, B of them must be collinear, actually exactly gives us the MCA property that we need. All right? So that's kind of a good thing to remember. And from this now, we know that the Reed-Solomon code is line decodable. From that, we can just derive the MCA error for the Reed-Solomon code. Yeah. So here you can see this is basically a classic bound now for the Reed-Solomon MCA error bounds up to the Johnson bound. All right. So of course, if the field is sufficiently big, this MCA error will become negligible. Okay, great. And so again, the challenge now is kind of the thing that we want everybody to think about is basically what happens when the distance goes above the Johnson bound. What happens to the MCA error? That's really what the proximity challenge is all about. Prove that basically the MCA error is small even when delta is above the Johnson bound. So up until the Johnson bound, we have these really elegant bound. This is based on the results just from last November. And so the question is what happens above the Johnson bound? And that actually takes us back to the grand challenge. So the grand challenge basically says find the largest distance such that the MCA error is still negligible, and hopefully now the words make sense so you can kind of understand what the proximity challenge is all about. Okay, good. So what's known about this? So effectively we know, as we just said, we know that up to the Johnson bound for a Reed-Solomon code, we know the epsilon that the MCA error is negligible for a large enough field. We know that roughly above the capacity of the code, we know that that MCA fails. In other words, the MCA error actually sort of blows up. And the real question is what happens in between. Yeah, that's exactly what the proximity challenge is about. And what we're hoping is that the MCA error is still negligible as we get closer and closer to the capacity of the code. Yeah, that's kind of a summary of what's known and what the challenge is about. All right, make sense? So we'll see if anybody solves this by the end of today, but that would be pretty cool. This is a pretty hard problem, actually. Yeah, so it'd be really nice to see progress on this. So let me summarize this one more time. So here again is what's known. We know that below the unique decoding distance, we know that we have very good MCA. We have very good bounds on the MCA error. Up to the Johnson bounds, we know that we also have decent bounds on the MCA error. We know that roughly at the capacity of the code, the MCA error breaks down. This is based on a very, very cool negative results. Yeah, so the MCA error sort of blows up next to capacity, and the question is sort of what happens between these two bounds. That's literally the $1 million challenge. Yeah, so it's a nice summary of what's happening. Okay, good. I want to say a few more things about MCA errors, and then I'll talk about the applications of MCA. Okay, so let's see. So the Goyal and Guruswamy paper, actually, what they actually prove beyond defining line decoding and its connection to MCA, what they actually prove is that there's a whole bunch of codes for which the MCA error is small up to capacity. Yeah, so the challenge is solved for many families of codes, except for the codes that we're most interested in, except for the Reed-Solomon codes over smooth domains. So in particular, they showed that for folded Reed-Solomon codes, MCA error holds up to capacity. So the proximity challenge is solved for folded Reed-Solomon codes. We know that for random Reed-Solomon codes, when the evaluation domain is random, MCA error holds up to capacity. So for that code, the proximity challenge is solved. The only problem we have is bounding the MCA error up to capacity for a particular evaluation domain. Yeah, for these smooth evaluation domains. For these variants, we know that the problem is actually solved. So One very natural question to ask is, well, what happens if we try to build a snark out of these codes where the MCA error actually holds up to capacity? So the random Reed-Solomon code, unfortunately, is not very good for snark systems. Why is it not very good for snark systems? Yeah, maybe it's too easy a question, but why is it not easy? Why is it not helpful? Yeah, exactly. The encoding time is quite terrible. However, it turns out folded Reed-Solomon actually have pretty good encoding times. Folded Reed-Solomon, the encoding time is pretty much the same as regular Reed-Solomon. And we just said that folded Reed-Solomon, the MCA error holds up to capacity. So the natural question to ask is, well, what happens if we try to build a snark out of folded Reed-Solomon? So Giacomo actually did a lot of scripting and calculations here, and it turns out actually, oddly, folded Reed-Solomons don't give us very good snarks. Actually, in fact, for folded Reed-Solomon, for the MCA error to be small up to capacity, we have to use a folded Reed-Solomon code with a very large alphabet. And it turns out the very large alphabet negates the fact that the MCA error can be larger than what it is for the regular Reed-Solomon code. Yeah. So there's an amazing open problem here, which is to try and actually either improve the alphabet size for MCA error up to capacity for folded Reed-Solomon, or maybe try to use folded Reed-Solomon in some other way to build better snarks. Today, they don't give better snarks, but there's an amazing open problem to try and get them to build better snarks out of them. I will mention a recent result that suggests that maybe the alphabet size is inherent. We're not going to be able to shrink the alphabet size for folded Reed-Solomon, but there may be other ways around that. Okay, so remember my rule of thumb: every talk is supposed to have a proof and an open problem. So here's your open problem. Try to build snarks, good snarks up to capacity using folded Reed-Solomon. Okay, cool. So the last thing I want to do, I guess I'm running kind of out of time, I want to quickly show you why MCA is such an important tool in the design of snark systems. Yeah, so why do we care about, why is the Ethereum Foundation paying so much money to resolve this MCA problem? And to do that, let's just look at one example protocol. I guess it comes up very naturally in Weir and in other, other snark systems. So yeah, so let's just look at an example problem. So suppose we have a linear code C, again, it's a subspace of f to the n, and the problem we want to solve is the following question. So here the verifier basically has two code words, U0 and U1, that are presented to the verifier as oracles. The verifier has another vector S and two values T0 and T1. What we're trying to do, what the prover wants to convince the verifier is that U0 and U1 are delta close to code words, and those code words actually satisfy some linear constraint. So it's not just an IOPP. It's not just proving that U0 and U1 are close to code words. The code words that they're close to are also satisfy certain constraints. And I guess Ali is going to talk about this question also later in the day today. But I want to kind of give you a brief overview and to explain why it's connected to MCA. So is the problem clear? We have these two code words words U0 and U1. We want to prove they're close to code words and that the close by code words satisfy a certain constraint. You can see the constraint here is that the code word inner product of vector S happens to be equal to this value Ti. All right, so let's look at a very simple protocol. The first thing that comes to mind, I mean, in the design of snarks, I guess there's really only one idea. What's the one idea? It's usually random linear combinations. Yeah, I guess recursion is another idea. But the main idea in designing snarks is random linear combinations. And so let's just do that. So let's design a protocol for this problem. So the protocol works by the verifier sends a random value. The prover is going to create a random linear combination of the two close by code words. It's going to send the resulting code word back to the verifier. The verifier is going to do some spot checks. So it's going to choose some positions x1 to xl, and in those positions, it's going to do spot checks to check that the code word really was a combination of U0 and U1. Okay, that's the whole protocol. So we want to prove that two words are close to the code. We take a random linear combination and prove that the result is close to the code. Okay, so far so good. This is complete if, in fact, UI happens to be a code word, which is good enough. And the question is, why is this protocol knowledge sound? Yeah, why can we extract the close by code words that satisfy the linear constraints if this protocol, if the verifier accepts in this protocol? Okay, this is like I would say this is like the simplest protocol you can imagine for proving such a statement. So we just want to be able to analyze this protocol. All right, so let's build an extractor. Let's build an extractor, and you'll see that MCA pops up very, very naturally in this question. Okay, so how is the extractor going to work? The extractor is given the verifier's view. So it's given U0 and U1. And its job, it's also given the random linear combination Z, and it's given the code word that the prover sent to the verifier. The extractor's job is to output now two code words that satisfy the linear constraints. So the code words have to be close to U0 and U1, and they have to satisfy the linear constraints. So what is the extractor going to do? Well, it's going to find some sort of agreement. It's going to look for the error positions between the code word that the prover gave and the linear combination and the linear combination of the two words that the verifier was given as input. Okay, so it's going to find the locations where there are errors. Yeah, that's kind of easy to do. You just kind of go position by position and see if there's an error or not. Okay, so far so good. What does this set have to do with anything? Well, because C is actually a code word, and because we did all these spot checks, we know that the linear combination is actually S delta close to the code with very high probability, right? That's actually what the spot checks prove for us. All right, so far so good. Well, because of that, because the linear combination, this is a point on a line, yeah? This is some point on a line generated by U0 and U1. Because this point on a line happens to be S delta close to the code C, the MCA property, by definition, implies that the generators of the line are also S delta close to the code C. That is exactly the MCA property, yeah? So the fact, again, we know that U0 plus ZU1 is S delta close to C. We know that the generators are also S delta close to C. Yeah, again, that is literally the MCA property. The cool thing about that is that now, because the extractor was able to compute this set C, this set S by itself, effectively the extractor knows exactly where the error locations are in the words that were given to the verifier. Yeah, so the MCA property, kind of, I don't know, I thought this was really cool. It's a really, really nice consequence of the MCA property, is just by looking at where the errors are in the linear combination, you can deduce, you can kind of learn yourself where the errors are in the generators U0 and U1 of the line. So now the extractor knows exactly what the error locations are, and so to recover the code words, all it has to do is just do erasure detection. Right? It knows where the errors are, so now the problem of recovering the code words is a fairly easy problem of erasure correction rather than list decoding. You don't need to decode, you just need to recover from errors at known positions. All right? That's what the MCA property lets us do. And of course, once you error correct, you output C0 and C1. So as a result of this, we get very simple extractors that use erasure correction as opposed to list decoding. So this is why it's such an important property. If you look at the extraction theorem, so what is the probability that this actually works? I can tell you that the probability that the extractor fails is bounded, you can see, by the MCA error plus some list decoding bound. And contrasted this with the number of spot checks that we do. So we did T spot checks, each at a distance delta. So the probability of failure here is going to be, the probability that the spot checks fail is going to be at most 1 minus delta to the T, which means the larger the distance that we can handle, the smaller the number of spot checks that we need. The smaller the number of spot checks, the shorter the snark proof will become. Okay, so we want to have a large delta so that we have to do few spot checks so that the proof is shorter. But the larger the delta is, the bigger the MCA error and the list decoding error are. So this is exactly why we need to understand exactly how the MCA error behaves above the Johnson bound so we can go to distances that are above the Johnson bound. So we want to kind of maximize delta so that this term is smaller, but we can't maximize delta too much if we can't bound the expression on the left here. And that's where the $1 million prize is, right? The $1 million prize is really to help us maximize delta and still be able to bound the expression on the left. Okay, so the goal here is to be able to bound the MCA and list decoding errors for the largest possible delta. That's the goal. Yeah. And so why this is true, this is in the paper, and I just want to point out we need bounds on MCA and list decoding for delta greater than the Johnson bound. Yeah, that's kind of the problem. All right, so to conclude, I want to remind you again, there's this amazing prize. There aren't that many prizes in mathematics. Yeah, so this is kind of an amazing prize. The Ethereum Foundation, I think, did something really quite beautiful there. $1 million prize for bounding the MCA error above the Johnson bound. Yeah, hopefully, some of you can work on this. It's a really fantastic problem. Encourage your colleagues to work on this. Help us solve this problem. What I will say is, please work on it. It's fine. Please work on it. It's fine to use whatever tools you want to work on this problem. What's not particularly helpful is to post a lot of what I would call AI slop that claims that the proximity problem is solved, as that is going to confuse a lot of the incoming researchers, and it's just going to cause a lot of work for us and a lot of confusion in the community. So just please make sure that when you post papers, the papers are correct, and we can hopefully help you do that as well. All right. So with that, let me conclude. I'll say that there's a lot more information. I only kind of touched on this topic a little bit. There's a lot more information in the paper. If you want to learn more, please take a look at this at the kind of the survey paper that defines the challenge. There's lots of open problems in the paper to work on. Lots of beautiful open questions. I think I already mentioned this question of can we build better snarks using folded Reed-Solomon? There's also this wonderful question of can we do better? Can we build better codes using non-Reed-Solomon codes? For example, LDPC codes. And so we would need better MCA bounds for LDPC codes as well. So we'd like to encourage people to think about MCA bounds for LDPC, and I think and that's basically the end of my talk. So hopefully we'll see progress on this problem in the coming year, and the world will be a better place. So thank you very much, and I'll stop here.
Okay, we have maybe a few questions on the topic. I will start with one question.
Yeah.
How does it feel to bring money to this to this game? Like, is this a common thing that mathematicians all of a sudden decide that this thing is worth $1 million to solve?
I guess this is not the only problem that's worth $1 million. We do have these millennium challenges that are also worth $1 million each. Yeah, so we have seen things like this before.
But this is commercially motivated $1 million, right?
That's fine. This is a pure question about polynomials. Yeah, so forget about the commercial applications for a second. It's just a question about polynomials.
Okay.
Anybody can work on this and solve it, and you'll get a prize. I think the bottom line is I think that the fact that there is a prize is mostly used to focus attention on the question. Yeah. Somebody actually, it's funny, I gave this was a bit of a technical talk to describe the prize. I gave a very, very high-level talk to a non-technical audience about the proximity prize. And I guess I did too good a job, because at the end of the talk, somebody raised their hands and said, well, if this is so important, why is it only $1 million? Shouldn't it be $10 million, $100 million? Yeah, and my answer was, mathematicians actually don't need that much money to get motivated to work on a problem. Really, this could be $100, and it would get just as much attention. So thank you to the Ethereum Foundation for devoting so much capital to this. But I think the goal of the prize is mainly just to focus attention on the problem. The actual number maybe matters less. Yeah,
Do we have
good question.
Question in the... There, I'll get to you.
Thank you. You mentioned this curve decoding. Are there any proof systems that use it?
Yeah, actually, curve decoding comes up as soon as you try to batch more than 2 words. Yeah, so if you try to batch 10 words, typically you would batch them using powers of a random linear value, and that immediately brings you up to like curve decoding for degree 10 curves. Yeah, so curve decoding comes up very, very naturally. So I just use line decoding for simplicity, but really curve decoding is really what we care about.
Thank you.
Yeah, good question.
So foldable RS codes are efficiently decodable.
Yes.
And they have good properties.
Yes.
So is there what makes them efficiently decodable, and is there a generalization of them?
Sorry, they're officially encodable because they're just as fastly, the encoding, doing the folded Reed-Solomon
decodable.
encoding is just as fast as regular Reed-Solomon.
Yeah.
And like I said, the amazing property is that they're list decodable up to capacity, and the MCA error also holds up to capacity.
So the question is, would we expect there to be a generalization of foldable RS codes for which both of those properties are still true?
Yeah, this is this subfield, what's it called? Subspace the design codes. There is a generalization.
I see. Okay.
There's a so foldable Reed-Solomon codes are one instance of a much more general set of codes called what is it? Folded, what is it? Yes, the subspace design codes. Yes, here. So these are folded Reed-Solomon codes are just an example of a subfield design codes. That's a very, very large class of codes. And for all of those codes, we don't always have efficient encoding for those codes, but for all of those codes, we know that list decoding holds up to capacity beyond Johnson, and MCA error holds up to capacity beyond Johnson. So all of those, there's a huge opportunity for using all of those provably in a snark without making conjectures.
And the result on the large alphabets is only for the folded Reed
only for the folded.
subset.
Yeah.
Got it.
So the
so there's an obvious open problem there.
Yeah. So if you can, for example, prove that folded Reed-Solomon holds up to capacity with a smaller alphabet, that would immediately improve the size of the snarks. This paper that I cite here at the bottom suggests that maybe that's not possible. Yeah.
Or a subfield design code that is not folded Reed-Solomon that doesn't have the same disadvantage.
Exactly. Yeah. So, yeah, there's a lot of greenfield questions to explore here.
Hey, just to verify, so the proof that line decoding implies MCA,
Yeah.
that proof works for all delta, even beyond Johnson bound.
Yes. Yes, exactly. This is as long as your as long as your line decoding holds with n+1 on the B side, then you immediately get this implication for MCA.
Okay, good.
Yeah. No, it's a very robust lemma. Yeah, it's quite elegant.
Any questions in the back?
Actually, now that I'm staring at this proof, would this generalize even for the curve?
Yes. This
version of this.
Yes. This holds for curves
see.
as well. Yeah.
Okay.
Yeah. It was easier actually for curves. Actually, the expression is a little bit. It's a good point. So if you have a curve of degree d, then you just need to replace n+1 by dn+1. So for curves, you need a slightly stronger linear decodability property, but it's basically the same property. Yeah.
So surely you and the judges have thought about how to potentially solve this problem. So I'm curious your thoughts and why this is a hard problem and why you haven't solved it yet.
Oh, okay. Yeah, Joachim, well, how come you haven't solved it yet? Yeah, I think the reality is if you look at the two challenges, then there's one challenge on MCA error, there's one challenge on list decoding bounds. Those, even though one doesn't imply the other, there are a lot of connections between the two. So resolving the MCA question probably is going to also have implications to list decoding, resolving the list decoding challenge. The list decoding challenge, this is a pretty old question about Reed-Solomon codes. I'd say this is like years old. It dates back to like even the history of the prehistory of coding theory, 60s, 70s. So this is a pretty difficult question. And because they're connected, this would probably suggest that this question is not going to be easy to solve, but that doesn't mean that it's impossible. We just need one new idea. Yeah. So yeah, please do it, Chelsea.
Okay. Thank you very much.
Great. Yeah, thank you.
So Dan, we see you again right after the break. We have Justin talking about the impact of the new results on of quantum on ZKP field in general, and then I'm gonna need your help to ask questions about this topic. So you'll join us then, right?
Right. Yeah.
Awesome.
Lots to say about quantum.
And for IOP Fest, we will be meeting back at 2 o'clock in the room nearby.